I warmly welcome you. Today we will solve a simple task using the Clebsch method. Specifically, we will focus on calculating the deflection at point B and the rotation angles at point C of a beam like the one in the drawing. We are given E, which is Young's modulus, 205 gigapascals, and the moment of inertia of the cross-section, 171 centimeters to the 4. We will start by recalculating Young's modulus and the moment of inertia into stiffness. This will be needed at the very end of the task, but if we do it now, we won't have to remember it later. EI is equal to 205 gigapascals, 205 giga, which is 10 to the 9, times 171 centimeters to the 4, which is 10 to the minus 8. We converted gigapascals to pascals, cm to the 4 to m to the 4. We put this all into the calculator. 205 times 171 times 10 to the 9 minus 8. We get 350550. What is it? A question for 100 points. We had gigapascals and meters to the 4. Let's do a quick unit calculation, so that we know later what unit it will have. Pascal is a Newton per square meter. We remember or don't remember from high school. So we got 350,550. Newton per square meter times meter to the 4th. The meters cancel out and we get Newton meter square. And as you probably remember, it's much more convenient to write newtons as kilonewtons in most of these problems. So I moved the decimal point 3 places and we get 355 kilonewton meter squared. These were preliminary calculations. We proceed to the main content of the task. First, we need to calculate the reaction at support A and support D. The system is statically determinate, as can be seen accordingly. We won't spend too long thinking about how to do this. In theory, we should already know. It is known that at support A, we only have one vertical reaction. At support D, we have both vertical and horizontal. But we will quickly calculate the sum of projections on the x-axis. As you can see, we only have HD, so HD is 0. And now, the next step is to calculate the reaction. Let's say we calculate VA by taking the moment about point D. VA times 468 meters. Plus the moment applied at point 5. Plus force 20 times distance 6. Minus 10 times 4 times 4. Distance from the center of load to point D. Minus 15 equals 0. I'm running through this a bit because it's something we theoretically all know how to do. If we do not know how, well, we need to go back to determining the support reactions. We get 6.25. Obviously Kn. And now, if we are absolutely sure that we actually calculated it correctly, then we can move on. However, if we are not sure, for safety, let's sum up the moments at point A. So we have 5 minus 20 times 2, plus 10 times 4 times 4, minus 15 and minus VD times the distance to the examined point. 4, 6, 8 equals 0. VD equals 0. So we quickly enter it into the calculator. It comes out to 13.75, which gives us some hope that it is solved correctly. Because if we now do the sum of projections on the y-axis, we get VA plus VD plus 20 minus 10 times 4. And indeed we see that when we substitute VA and VD, it gives us here 20 Kn, plus 20 gives 40, minus 40 gives 0. So we calculated the reaction correctly. Yes, because it is worth doing this check. You can still make a mistake even in simple math. Okay, since we already calculated the reaction, we move on. We move on to writing down the bending moment equation. Because we used Clebsch's method here, we remember that in Clebsch's method there are these two magic tricks. The first trick is related to moment distances, but that will be in a moment. And now the second trick is related to the fact that if we have a continuous load, we must extend it to the end of the beam. Translating this from Polish to our language, we have something like this. We calculate the moment with respect to such a cross-section. In the farthest section, that is, in section C, this is the point with respect to which we need to calculate the moment. But because we want the equation we write to be valid for every section, we need to write the moment with the extended continuous load. We extend the continuous load to the end of the beam, but we know it is not really there. Therefore, on the opposite side of the beam, we apply a continuous load with the same value in the opposite direction. So here too we have a continuous load with a value of 10. I now write the bending moment with respect to this point of intersection. Just as if I were calculating a regular diagram for beams. Mg is equal to, well, the first thing is we have VA times x. That via the x distance with respect to the point of intersection. That is standard. Now will be the first trick. Plus 5. And now, attention, times x to the power of 0. Why? One could say just because. In the Clebsch method, if we have a concentrated moment, at this point we take the distance, raise it to 0, and we enter it into the moment equations. But why do we have to do it? Because we will be integrating this equation shortly. And although for this 5, for our moment m1 it will not matter. Because when we integrate that, we'll still end up with 5x. Then 5x squared over 2, etc. Then it will matter a lot for moment m2. But we'll get to it in a moment, and we'll talk about it. Then we have 20 times x2. That's 20 the distance, meaning the x distance minus 2 meters. You can also remember it as a mnemonic. Here we always have the position of the force application point, or the starting point of continuous loading. So now, when we have continuous loading, minus the loading value, that is 10 times x. For now we've written down the resultant, but it's not times x, but times x2. Because we see that this load does not start at point A. It does not start at x-coordinate 0, but it starts at x2. Because for now we have it. Along with this pink section. Notice this is supposed to be the extended load. So here we have something like this. Let's say it's roughly in the middle by I. And here we have 10 times x2. Because that's this little section. This is our x2. And of course times x2 over 2. Because we remember that the resultant of continuous loading is always located in the geometric center of the load. Obviously. Next, we have an applied moment with a value of 15. So minus 15. And here, pay attention to this. We have x6. If we didn't add this x6 to the 0 power, because this is a moment, then when integrating it would be minus 15x. But that's not how it works. We have to apply x6 to the 0 power. So that later w prime, meaning the angle of rotation, and w, meaning deflection, come out correctly. And of course, we take into account plus. Here, I will allow myself to note this continuous load in a shortened form. 1/2 times 10 times x6 squared. Notice that this is very analogous. This is actually writing 10 times x6 squared, but in a shorter form. All right, and now firstly, we have noted all the elements. Yes, VD and HD are already beyond the intersections, therefore we do not consider them. For VIA, we will soon substitute what we obtained, because now we are substituting into the deflection line equation. In the differential form, EI times W bis equals minus mg. The minus is related to the reference frame we are adopting. We won't delve deeply into this now, but let's remember one thing, that what we calculate will be relative to such a system. In the positively directed vertically downward. The x-axis, because we already know it is directed to the right. But the important thing is that the angle of rotation will be directed clockwise. So this is our positive rotation angle. Let's call it phi, or otherwise w. Now I rewrite the same equation, changing the signs and substituting what I can. Which means I have minus 6.25 times x minus 5 times x to the 0, minus 20 times x minus 2 plus. And now notice I will write 5 times x minus 2 squared. I've already simplified it, multiplied what I could. However, we should not, heaven forbid, open these brackets. So we don't multiply any expansion formulas or anything like that. These brackets should remain in this form in Clebsch's equation. Plus 15 times x minus 6 to the power of 0, minus 5 times x minus 6 squared. And now, there are two schools of thought. Personally, I often tell students that it's not necessary to note which section is which, because it's evident from what is inside the brackets, right? But here, since some instructors require it, let's note that these two terms, which are minus 6.25x minus 5x to the 0, belong to the AB section. Next, this belongs to the BC section. And of course, this belongs to the CD section. Why is this important? Because soon, when we are noting boundary conditions, or when we want to calculate the deflection values or the angle of rotation for a specific point, it will be hugely significant whether we should consider a particular term in the equation. You'll see shortly. I am integrating, which sounds scary, but we know these are trivially simple integrals. So, minus 6.25 for x. We have the integral of x, which is x squared over 2 minus 5. The integral from x to 0 is x. Interval AB concluded. Minus 20 times x minus 2 squared over 2. Note that I am integrating this as a whole, right? Plus 5x minus 2 to the third power over 3. Again, I integrate it as a whole. If you have doubts whether it's allowed to do so, yes, it is completely allowed. And I refer you to the literature to verify why it's allowed. X minus 6 to the third power over 3. We denote this as CD. Remember the constants of integration, because this is an indefinite integral. Then we have EI times W, another integral. Minus 6.25x to the third over 6, minus 5x squared over 2. Note, again, I might have done this a bit too quickly here. We had x squared over 2. We have x to the third over 6. Why? Well, because it's really 2 times 3. It was x squared over 2. I calculated the integral. It should be x to the third over 2 times 3. 2 times 3 is 6. We can calculate that mentally. Minus 20x minus 2. Again, the same story. Let me expand it correctly this time. Plus 5x minus 2 to the fourth power. 3 times 4. I might as well write 12, but let's write it out in a detailed version. X minus 6 squared over 2. Minus 5x minus 6 to the fourth power over. And here I'll maliciously write 12 for a change. Interval CD concluded. Plus C, but I integrated C too. So CX, and a new constant. And we have the equation for the deflection line. We have the equation for the angle of rotation for any point. However, we don't have C and D. So how do we determine constant C and D? Constant C and D must be calculated from boundary conditions. Now, what are the boundary conditions for this type of beams? The matter is trivially simple. Once we realize that we can intuitively write out most of the boundary conditions, more interesting boundary conditions, or rather the stitching condition, will occur for a hinged beam. But that's for another occasion. So now what do we know about point A? There is a support there. Consequently, if we have a support, how much is the deflection? The deflection is equal to 0. The deflection at a support is always equal to 0, because deflection is nothing but vertical displacement. Here for us, and in this specific case. Therefore, we see that the support does not move up, nor does it move down. The support must always be at the same level. Consequently, the deflection at the support is equal to 0. And let me emphasize, it doesn't matter whether this support is horizontally movable or non-movable. We are talking about vertical displacement. Here, we will use only this condition. However, remember that when you have a fixed support, both deflection is equal to 0 and the angle of rotation is equal to 0. But then if you ever encounter a vertical roller, or more correctly, a movable fixed support, then only the angle of rotation theta is equal to 0, because something like that means that theoretically it can move vertically, Yet the angle of rotation at this point remains 0. So now how to use these boundary conditions? We have a support for x equal to 0, that's point A, and there the deflection is equal to 0. 0 deflection at the support at the point with coordinate 0 is the best thing that can happen to us in these tasks. Because look. Essentially, I substitute first only into the section in which the given support is located. The given support is located in the section AB, therefore I substitute only here. But even if I substitute only here, it still zeroes out. Thus, I have 0 plus 0. Of course, I will not write that. Now, we skip this part. We skip it firstly because the support A is not located in the section BC. It is located before this section. Therefore, we do not include it in this equation. Should you forget the rule that we do not consider this? Remember that what we have in parentheses is the force position. If you substitute 0 here, you will get 0 minus 2 meters. It is not really possible to be at minus 2 meters. Therefore, we do not substitute this into these elements. Let's move on to the constants. So we get plus 0 from 0. We won't be writing this either because 0 is 0. Plus d. So we get 0 equals d. How to remember this in an even simpler way? If we have deflection for x equal to 0 with a value of 0, then d will also be 0. Because what is d? D is precisely the deflection value for x equal to 0. And now the second condition is less pleasant. We have w of x equal to... Where is the second support? At point D. So point D has a coordinate from 0 looking. 2 plus 4 is 6, plus 2 is 8. So we have w for x equal to 8, also equal to 0. Unfortunately, point D is located in the CD range. So we consider everything from start to finish. Now we have to tediously rewrite it. And with a heavy heart, I am doing just that. Minus 6.25, 8 to the power of 3 divided by 6. Minus 5 times 8 squared divided by 2. Of course I substitute for x, right? We try as much as possible to simplify and shorten it immediately. Shortly, we will enter this into the calculator, so we try to make it as short as possible for input, to minimize the chance of making errors on the calculator. And I think I entered it correctly. D, of course, equals 0, so we don't bother writing 0 because it's pointless. And now we calculate C, so we input it into the calculator. We get like this, minus 6.25 times 8 to the power of 3 divided by 6. Subtract 5 times 8 squared divided by 2. Subtract 20 times 6 to the power of 3 divided by 6. Add 5 times 12 to the power of 4. Add 15 times 2 squared divided by 2. Subtract 5 times 2 to the power of 4 divided by 12. We get minus 850. Running out of space a bit. Let's mark the equations we won't be using. From the moment equations, we definitely won't use them. And we probably won't have to use the equation Wobesa for this task anymore. So now we have minus 850. Add 8c equals 0. So after complicated calculations, c equals 858ths. Now then, I won't do the unit conversion. Let's assume with faith that c will be expressed in kn times and tm to the power of 2. And neatly. And now, we already have everything we need for happiness. So we can calculate the deflection at any point, the angle of rotation at any point. We are specifically asked in the task. Calculate the deflection at point B. So if calculating the deflection at point B, then we write that WB equals W from x equals 2. And now, where do people very often stumble? By forgetting that we still have EI on the left side. We could forget about it when the deflection was equal to 0. But now we must remember that we move this EI to the right side. We have 1 over EI, where EI is the stiffness, which we calculated at the very beginning, and it takes its place in the top right corner. And now we insert it. And now, Point B, as the name suggests, belongs to the interval AB. Therefore, we enter it here. And we remember about C. Minus 625. X equals 2. That 2 to the power of 3 over 6. Minus 5, 2 squared divided by 2. And plus 6, that is plus 850 over 8 times also 2. Quickly enter this into the calculator. Minus 625 times 2 to the power of 3. Divided by 6 minus 5 over 2 times 2 squared. Plus 850 over 8 times 2. It comes out in the so-called mean time, which does not exist. I'll quickly check if it came out the same as when I calculated it earlier. I think it did. 194.17. Now then, we also substitute with EI. We substitute 350.55. Now attention, attention. What's on top will have the unit of K&M to the third. And here we have K&M squared. Therefore, the result will neatly come out in meters. It came out to 0, 5,539 m. Of course, I hesitated for a moment because these tasks, as far as I remember, I think I wrote them myself. I won't hide that it's not the smartest result in the world. It is not very related to reality. We got a deflection of 55 centimeters. It's known that in engineering practice, if we get a deflection of 55 centimeters somewhere, we start to get quite worried. Here it came out as it did. In such a case, the cross-section should be increased. Then, by dividing by greater stiffness, we will get a smaller deflection. The result is numerically correct. Therefore, we move on to the next issue. We need to calculate the angle of rotation at point C. By the way, if such a task were assigned on a quiz somewhere, or on an exam, and they asked for a comment on the result, I would then comment on the result as follows. That a different cross-section should be adopted. That is, for example, change the section to a larger one. Because that stiffness, as you can see, does strange things to this cross-section. This is something we don't want in engineering practice. All right, the angle of rotation at point C will probably be funny too. Phi C is W for x equal to, where is point C x equals 6. So let's go ahead with substitution then. But now, attention, we do not substitute into E and W. We substitute into E and W, because W, as we have determined, is deflection, and W is the angle of rotation. Therefore, we now substitute into the angle of rotation equation. 1 over E, and remember why. Minus 625 times 6 squared over 2. Minus 5 times 6. Minus 24 squared over 2. Plus 5, 4 cubed. Sorry, 4 to the third. And that's it, because point C belongs to section BC. So we take BC and everything before BC. We don't take from this, obviously, even if we substituted it. So we have x equal to 6, 6 minus 6, 0, 6 minus 6, 0 plus c. And then we take plus 858. We quickly throw it into the calculator. Minus 6, 25 times 6 squared over 2. Minus 5 times 6, minus 20 times 4 squared over 2. Plus 5 times 4 cubed in space. Plus 858. We get minus 89.58 over EI. EI is 350.55. Quickly, the units. Kilonewton times meter squared divided by kilonewton times meter squared. Sees nothing. In practice, we will get radians because we know this is the angle of rotation. So we end up with 89.58 divided by 350.55. Which is 0.255 in negative radians. Which also shows us that this result is not very possible to exist in reality. We can, for it to be illustrated, because for most people, something coming out as 0.255 radians is like, well, great that I got that. What does that mean? We'll see it in degrees. We'll see why this result isn't rational again. We remember how to convert to degrees, I hope. 14.6 something degrees. So if our cross-section rotated by 14.6 degrees, it is quite reasonable to start worrying. Nevertheless, this is the end of the task. We have calculated the deflection at point B and the angle of rotation at point C as per the content. So thanks a lot for listening. I hope it can be understood better, simpler, faster now. And as usual, we kindly recommend ourselves. Until next time.